Yeah.
Okay, questions? So we're looking at Sn1 and Sn2. No questions?
Question 7.25.
725, okay. Chapter 7. Okay. Did I do that one? And so you were delegated to ask the question?
Yes.
Okay, let's see, 7.25. Where is that? Closer, there. Okay, which would undergo, since this is chapter 7, Sn2 fastest? So let me copy it and paste it into there. Okay, so this is an Sn2 reaction. So which halides undergo Sn2 the fastest? Or better yet, what is the reactivity of the alkyl halide based on in Sn2? So in other words, what makes one alkyl halide go faster, react faster than the other? Okay. Sn2. What are the big things about Sn2 to review? What's the rate equation for an Sn2 reaction? The rate equals K times concentration of what? And we're taking a nucleophile, we're reacting it with an alkyl halide, we're substituting the nucleophile for the halide ion. So what's the rate of that reaction? What's the rate equation?
The concentration of the nucleophile the first order times the concentration of the alkyl halide to the first order.
first order in each. That means the concentration of the nucleophile, the concentration of the alkyl halide, even the concentration of the leaving group, when this isn't a halide, is going to play a role in the rate of the reaction. Okay. What's the mechanism? How many steps in the mechanism? Give me a number. One. There's one step in the mechanism. It's a one-step concerted mechanism where the nucleophile will come in, attack the carbon, the leaving group leaves, we end up with a single transition state, which is going to be trigonal bipyramidal, and then we end up replacing the halogen. We're just reviewing the big things here. Or maybe it's more than review. Hopefully it's not more than review. Okay, here's an Sn2 reaction of 2-bromobutane and hydroxide. What is the final product going to be? Is the final product going to be R or S? So if you need to discuss in groups, discuss with the neighbor. Tell me what the final product is going to be. RS. Or 50-50. Are we ready to vote? Okay, we ready to vote? R is A, S is B, C is 50-50. I guess D is, don't know. Your hand has there. Okay. Okay, let's see what we've got. We've got 8 R's and 13 B's, and I think we have more than 21 people here. Maybe not. Okay, so we've got 8 and 13. Question number 1, what is the stereochemistry of the reactant? Is it R or S? Let's vote again. Let's vote on the stereochemistry of the initial product, or of the initial reactant. Is it R, A, or is it B, S? Can't be 50-50 in this case. That it is R. Is it? Should probably always check. Number 1 priority group here. Somebody say it. What? Bromine. Number 4. Hydrogen. Number 2. Ethyl. Number 3. Methyl. 4 is away from me, right? Going from 1 to 2 to 3 is clockwise. So I'm starting with R. Now, in an Sn2 reaction, when you start with an optically active chiral molecule, what is the product that you get chiral? Or is it achiral? For Sn2. Chiral reactant gives you a in Sn2 is when you react a chiral molecule, do you get A, a chiral product, or B, a non-chiral molecule? Yay, 22 chiral. You get a chiral molecule with what happening to the chiral center? It gets switched, inverted. So in other words, what should be the final product over here then? Sn2 undergoes inversion of configuration. So the final product over here should be S. That's what happens in the backside attack. So if I was to write this product, what I would do is, well, what I should do probably is just write the entire mechanism here. So I'm going to take my hydroxide, I'm going to react it with my carbon, with my hydrogen, my CH3, my bold wedge CH3, CH2, my bromine, so that this comes in, kicks off the bromine, but now let's write the stereochemistry of the trigonal bipyramidal geometry, which will always look like this. Nucleophile on the left, dotted line to the carbon, dotted line to the leaving group. The other three bonds are going to basically be trigonal bipyramidal, but wherever the group is, it's going to stay on that bond. So the CH3 stays on the bond in the plane, the hydrogen goes on the bold wedge, and the CH2-CH3 group goes on the dashed wedge, the ethyl group goes on the bold wedge. So that would be the transition state. The hydroxide is delta minus, the bromine is delta minus. And so that is my transition state showing the stereochemistry. I put sort of a skeleton around the dotted, or the dashed wedge, because dashed wedges look an awful lot like dotted lines. Okay, so now the bromine gets kicked off the rest of the way, so it's going to be a Br minus. Then what happens is my carbon ends up with the OH on the left in the plane. Then everything else follows. Then everything else follows in the place where it should be, or where it started out to be. Like that. Okay. So the inversion of configuration says that if you start with R or S, you're going to get the opposite. But because this reaction has to go backside attack, as long as you're replacing the number 1 group as the leaving group with the number 1 group as the nucleophile, it will always go then number 1, number 4, number 2, number 3. 4 is away from me. I'm going counterclockwise. So in this case, the final product is S if the initial molecule started out as R. Okay, so you always undergo inversion of configuration. And so that's Sn2. So that's big idea number, well, this is 1. The mechanism is number 2. The stereochemistry is number 3. So this is the big thing for Sn2, number 3. Number 4 is reactivity. So number 4 is, how about the reactivity of the halide? Okay, since it's a backside attack, a concerted means one step bond making, bond breaking in the same step. Since this is a concerted mechanism, the reactivity is going to be based on how quickly, how efficiently, how low of energy can the nucleophile get to the carbon in the backside attack, and ultimately the reactivity is based on the energy of the transition state, because that gives you the activation energy. And if we remembered all the way back to general chemistry, we have this little equation that says rate equals A times e to the minus EA over RT. That is the Arrhenius equation. And the Arrhenius equation is what gives us the mathematical relationship between reaction rate and activation energy, and reaction rate and temperature. It is not linear, it's logarithmic, so that The lower the activation energy, the faster the reaction. The lower the transition state energy, then the lower the activation energy, the faster the reaction. Why am I saying it that way? Because the activation energy is going to be related to the structure and energy of how easily the nucleophile can backside attack and kick off the leaving group. What's that based on? What's that going to be based on? I could see, I anticipated two answers. Number one, basicity, if we're looking at the strength of the nucleophile, or if we're looking at the leaving group ability. So yes, basicity would play a role in terms of having a stronger nucleophile or having a leaving group that is a better leaving group versus a worse leaving group. Okay, at this point I should ask, leaving group, what makes a good leaving group? A leaving group is a blank base. A weak base, or a weaker base. So remember, leaving group ability is based on one thing, basicity. How? Inversely. Okay. Nucleophile strength is going to depend, right? If it's a horizontal relationship on the periodic table, the nucleophile strength is based on horizontal relationship. Nucleophile strength is based on basicity. Vertically, it's based on polarizability. So, yes, the reactivity of the alkyl halide will be based on the strength of the nucleophile and the strength or poorness of the leaving group. However, that's not what this question asks, because this question all has a bromine leaving group, and it has the same nucleophile, which is this ethane thiolate group. So there's no difference in nucleophile for all these reactions. There's no difference in leaving group. So the question that I ultimately started with here is, well, what is different about this? And the difference here is, what kind of carbon is each of the bromines, or are each of the bromines attached to? And so if I said, what kind of carbon is that bromine attached to? What would you say? What were you mouthing, Caitlin? Secondary. Do we agree? It's a secondary carbon? You might have been at the beginning like, what is he talking about? Sometimes valid question. But in this case, what kind of carbons are attached to the bromines? Our choices are primary, secondary, or tertiary. So this is what kind of carbon? A secondary. What is this one? Primary. What is this one? Primary. What is this one? Primary. Okay, that's not all that helpful, because the only thing that's different is secondary versus primary. But ultimately, it doesn't matter, because if I go back here and say, what Now with the alkyl halide, what's going to make the alkyl halide react faster, or better yet, what is going to make the alkyl halide react slower? Is there an alkyl halide that does not undergo Sn2? Which one? Tertiary. So a tertiary halide will not undergo Sn2. So that's a carbon with 3 other carbons attached to it. Why does it not undergo Sn2?
Because it's not possible for there to be a backside attack.
It's going to be really difficult to do a backside attack on this carbon. Why? Because this carbon is really sterically starts with H. Sterically hindered. That carbon is very sterically hindered. And so it's going to be difficult for the nucleophile to get to that carbon in order to transfer its electrons. We talked on last Wednesday, and I know that was last Wednesday, but it wasn't that long ago, of the idea that the reason for the backside attack is because the nucleophile has to take its lone pairs in this orbital and overlap it with the little teeny tiny sp3 orbital in order to form the transition state. Well, if there's a lot of steric hindrance around that, it's not going to be able to do that. And that's not even a good way of saying it. The better way of saying it is that the steric hindrance is going to cause this transition state to become more unstable or have a higher energy, which is going to make the activation energy higher, and at some point the activation energy is too high for the molecule, for the reaction to overcome. So steric hindrance means that the transition state is going to become higher and higher in energy. So if I want a reaction, an Sn2 reaction to occur, what do I need to not have around that carbon? Steric. Hindrance. Well, what kinds of alkyl halides are going to have the least amount of steric hindrance? The best one would be having just a methyl group, because then there's 3 hydrogens. You can't get less sterically hindered than 3 hydrogens. And then what would be the next? Well, the next would be to put 1 alkyl group on there and make it primary. And then next would be to put 2 alkyl groups on there and make it secondary. So we would expect a secondary halide to react the slowest. And of course, if we put a tertiary halide on there, what happens? You don't get Sn2 reaction. So as far as the halide goes, methyl reacts the fastest, then primary, then secondary, which is much more reactive than tertiary because tertiary doesn't undergo Sn2. So for an Sn2, that's the reactivities of the alkyl halides. And in the book, they kind of showed you the steric hindrance in terms of the nucleophile trying to get to that carbon. In my video and PowerPoint, I actually have the viewpoint of the nucleophile trying to get to the carbon. And the greater the number of groups, the harder it is for that nucleophile to get to that carbon to form the transition state. So as far as the halide goes, primary, secondary, primary is faster than secondary, which is faster than tertiary because tertiary doesn't undergo Sn2. That's the big thing, number 4 for Sn2. Right? Are we all okay with that? Were we okay with that before I just went over the explanation? Want an honest answer here. Is this kind of the first time that this makes sense? Yes or no? After I just went through this, the idea of the halides, primary versus faster than secondary, were we... I'm asking too many different questions. Did you understand that before I just went through this? So before, yes or no? Okay. How about now? Does this make sense? That primary, methyl's fastest, primary, then secondary, tertiary under now. Does that make sense to you? Yes or no? Okay. Right. So those are the big 4 things for Sn2. Are there any questions about those 4 things? Because those are the 4 characteristics. And so I'm going to, on Wednesday, I'll have a practice homework problem set where you're going to have to write the mechanisms for these reactions. So you're going to have to write an Sn2 mechanism like this one where you're showing the chiral center undergoing inversion. Okay? And the transition state. Right? So those were the 4 big things for Sn2. So if we go back to this problem here, let me give you I'll give you a couple minutes. Let's rank these. Let's finish off this problem. Go ahead, discuss, work with yourself, and then ask others. I'm going to ask we're ranking these from fastest to slowest. Okay? So I'm going to ask, we're going to go down the line. So which one is the fastest, which one is the slowest? I'll give you a couple minutes. Steric bulk and steric hindrance are basically the same terms. Okay, we ready to vote? And let's see, what do we want to vote on first? Let's vote on the least reactive. Which halide would undergo the reaction the slowest? And your choices are that number 1 is A, 2 is B, 3 is C, 4 is D. So which one is the least, is going to react the slowest or the least reactive alkyl halide? A through D is your choice. All right, so we have 24 A's. So A is the least reactive. Okay, so why did we make that choice? Because it's secondary and everything else is primary. Now, could you have made a choice? Well, let's continue. There was one number B and one D. And you could probably make an argument for either B or D, but based on secondary is the slowest versus primary, we would make the choice of A being the slowest. Now, the remaining 3 are primary. So which one would be the next slowest? Okay, so I want to go with the next slowest. We'll work our way up the list. So next slowest of B, C, or D. We've got 19 Ds. So we've got D with 19, and then 4 A's. I'm confused by 4 A's, but okay. So we've got 19 D's as our major answer. Okay, and then next, what would be the next one? And your choice there, now we're down to B or C. Because I'll accept D as the next slowest one. So then it's down to B or C. Okay, B or C. We've got 22 B's. And then that must leave C as the most reactive. So as you're making these rankings, what are you basing it on? What were you basing your rankings on? Okay, we have sticks with everybody's name on them. And when I push this button down here, it's going to randomly choose a stick with a person's name on it. That's going to cause undue stress. It may be causing undue stress right now of people knowing that I could push the button and choose them randomly. The way to avoid this is to provide me with an answer. So, what was my question? Because, see, I'm not supposed to do this because this causes stress to people that don't like to be called on. Despite the fact that I have not humiliated anybody in class yet, or have not tried to, it still causes stress when I would randomly call on people. Now, if I pick on somebody, then that's going to cause even more stress, except the people aren't being picked on. So I don't know what to do other than to ask the question again and say, okay, what was the basis for the rankings? What was it?
Steric hindrance.
It was the amount of steric hindrance. So with the C, there's two hydrogens in an ethyl group. Is that the best in these molecules in terms of being the least sterically hindered? Yes. Then over here I've got two hydrogens, but then what kind of group do I have here? An iso, close, isobutyl. And then over here, what do I have? A terse butyl. So going down the list here, the steric hindrance becomes more around that carbon. Despite the fact that they're primary carbons, they still have large groups attached to them. So the larger the group, the more steric hindrance. But again, I want to make this point. The larger the group, the more the steric hindrance. How does that slow down the reaction? That slows down the reaction because eventually the nucleophile has to come over here and form the transition state. Well, the transition state with all these large groups around it is going to go up in energy. As it gets higher in energy, the transition state, the higher the activation energy, the slower the reaction. So when we say steric hindrance and it kind of prevents the nucleophile from reacting, that's okay, but it's not the truly correct answer. Because in chemistry, the currency of chemistry is energy, right? You want to know why things happen in chemistry, you need to understand the energies. Right? You want to understand why things happen in politics, what do you need to follow? The money and power. Right? Chemistry, it's all about energy. And so in this case, that's why reactions will go slower or faster, is because they have transition states with lower energies or higher energies. But we can sort of cut through that and just say steric hindrance, or steric bulk, or sterics. The larger the groups around the carbon, the more groups, the larger the groups, the less reactive that alkyl halide is going to be.
They're both butyl groups. They just think one is steric and one is iso?
Yes. So basically, the terse butyl group around here would have more, would provide more hindrance than just the isobutyl. Because if the isobutyl, what I could do is I could kind of orient the isobutyl group down here away from where that carbon is going to be attacked. So if I orient it down here, you'd have a little bit better attack. But it's debatable as to how close these are.
Is there one in terms of like the second carbon and breaking that with
You could, but it really is about the carbon that's attached to the bromine. So we have to look at this. Yeah, but we have to look at that entire group. So isobutyl versus terse butyl would be bigger. This kind of question isn't. I mean, this kind of question is a little bit tougher because they're asking you to base your assumption on the size of the group. And so an isobutyl versus a terse butyl, there probably isn't that much difference. So you could probably quibble about where B and D are. But definitely C is first and definitely A is least. If you follow secondary is least reactive and primary is most reactive. And that's what I want you to get out of this. What's the reactivity of halides in Sn2? Primary fastest, methyl fastest, primaries, then secondary, tertiaries don't react. Inversion of configuration, bimolecular kinetics, meaning the rate is dependent on the nucleophile and alkyl halide concentration, and then the mechanism, the trigonal bipyramidal transition state that's formed. Those are the big four things. Okay. And if you need to look at those again, go to last Wednesday's video, and there are a number of videos that I would, what I should do is I just should assign you the video to watch. You should watch the video that's in the folder before coming to class. And then take a look at the book, and most of the stuff that's in the book will be a little bit clearer. There may be some stuff that I don't cover in the video, but that's where your first focus should be, is to watch the video that's there. Okay, sort of. Any other questions? So, Sn1. Let me just start by saying that we just basically said that in Sn2, primaries react faster than secondaries, and tertiaries don't undergo Sn2. But tertiaries do undergo substitution. So what is their mechanism like? All I can imagine is that people were studying the reactivities of alkyl halides with nucleophiles. And they found out that all the nucleophiles underwent substitution. But when they looked at the kinetics, they did primary and secondary and said, oh, well, the rate equation is concentration of halide, concentration of nucleophile, so that when they changed the concentration of each one of those, the rate got faster. But when they did the reaction of a tertiary halide, something like tertiary-butyl bromide, and they reacted it with hydroxide, what they found was that they still got the substitution, product, but when they measured the rate of the reaction, what they found was that they got a rate of, let's say, 10 when they used a 1 molar solution of alkyl halide and a 1 molar solution of hydroxide. And they said, okay, let's double the concentration of halide and keep the nucleophile concentration the same, and the rate doubled. And they said, great. First order in alkyl halide. And then they said, well, let's keep the concentration of the alkyl halide as 1, but now let's double the concentration of the nucleophile. And then they measured the rate, didn't change. They probably repeated that at least once or twice more. Then they said, well, let's try and triple the concentration of the nucleophile. And the rate stayed the same. And so they had to conclude that the concentration of the nucleophile was raised to the 0 power because anything raised to the 0 power is 1. And I could imagine them wondering what was going on. And so that, when the kinetics change, it means that the mechanism changed. In general chemistry, that's the importance of kinetics. If you're using kinetics to determine a mechanism, if the kinetics change, that means the mechanism changed. And so how did the mechanism change? Well, that's what they had to propose. And that's where the video for today, I think I go through this step by step. And I will on Wednesday if we need to as well. But that was the change in the mechanism. So on Wednesday, here's what we will do. There is a video for Wednesday on how to determine the difference between whether a nucleophile is going to undergo Sn1 or Sn2. How do we predict these reactions? And then the beginning part is, I believe, I can't remember. I just did this last night, but I can't remember exactly what the first part of the video is. From here, from chapters 9 and 10, I believe, are just various characteristics of Sn1 and Sn2. So we're going to be going over those various characteristics, some of which we already have. I think it might be solvent effects on Wednesday. What role does the solvent play? I've answered a couple of questions for Sn1 and Sn2 on Piazza, which I would encourage you to take a look at. So for Wednesday, what I'd like you to do is, if you haven't watched the videos for Sn1 and Sn2, please go back and do that. And then look at the textbook for chapters 7 and 8 about the various parts of this. And then if you could watch the video for Wednesday, so we'll talk about solvent effects if necessary. We'll talk about any of the Sn1 characteristics that we need to. And then that's what we're going to continue to do as we finish up. Well, then we're going to add in E1 and E2. But we'll talk about how do you determine the difference between Sn1 and Sn2 on Wednesday, okay? And I will be posting your scores from the homework problem or from the in-class problems. Remember, those are participation. I'll be updating the grade book because midterm grades, this year everybody gets midterm grades. Not just if you're at a C- or lower, and not just if you're a first-year student, or not if it says I have to give you a midterm grade. Everybody has to get midterm grades. They are just that, midterm grades. They're going to be dominated by your exam score, but they'll give you a chance to know where you're at, okay? I will take your Scantrons for the homework problems. I'll have those back on Wednesday as well. If you have any questions, email me, post on Piazza. I will update by the end of the day.